high quality data available every 5 to 6 minutes. I think we can actually get it in 4 minutes, every 4 minutes now. Well, maybe this is not like, maybe this is Umberto. I think this is Umberto of 2007. Definitely not Ike. So there are some disadvantages. Of course, this is only available when the storm reaches the coast or is near the coast. And it's not really a tool that we use in the forecast process. And the data that we see are not at the surface. There's not a one-to-one correspondence between what we're seeing aloft and what we see at the surface. So there are certain algorithms that we use to determine what the wind speeds likely are at the surface. Of course, these are estimations also, and there can also be the issue of range folding. Okay, and then we have the step frequency microwave radiometer, which I won't spend a whole lot of time on, but this instrument was actually used on some of the P3s back in the 1980s, and there wasn't a big push to start using this type of instrumentation again until most recently, because there's been a lot of success with other scatterometer type data. So what it does is it measures the microwave radiation emitted from the ocean surface. It's some measure of the ocean roughness, so the ocean surface gets rougher when the wind speed gets higher. And it can measure the max surface winds in the core of major hurricanes. For the SFMR, it actually gets more accurate when the wind speeds are above 50 knots. And it's less accurate when it's below 50 knots. So for major hurricanes, we heavily rely on the SFMR. And one thing to keep in mind, this is true for any of the reconnaissance data, but it's providing data along the flight track and nowhere else. So it's a sort of like an instantaneous shot of the storm structure. Of course, we can't tell what's going on at every point in time in the hurricane. So some key points here with regard to the reconnaissance data. With very, very few exceptions, direct observations of the maximum sustained winds are available in tropical cyclone. When we talk about aircraft, the aircraft, it measures winds at flight level along the track of the storm, and so they require quite a bit of vertical adjustment. Typically, a reconnaissance aircraft flying at 700 millibars, we use the 90% rule, unless there's some reason to deviate from that. Most of the aircraft fly at 700 millibars. If it's an invest, they'll fly much lower, maybe 850 millibars, which is 1,500 feet, and there are other vertical adjustments that we can use there. The dropsondes, which are released within the hurricane, they measure instantaneous winds, and they do require quite a bit of temporal interpretation because the dropsondes are moving around azimuthally around the storm center, and so that has to be taken into account. And there are some severe sampling considerations because of that. And as I mentioned, with the SFMR, it's the data that we're receiving are along the flight track, and they require quite a bit in the way of sampling considerations.
Todd,
yes?
You mentioned something about a 90% rule. Could you explain that to everybody, what that is?
Right. Actually, this is probably a good point to do that. After looking at a large sample of profiles from all types of storms, major hurricanes in particular, these were averaged. And I'd say, maybe we have a population of 400, 500, 600 cases, and we arrived at what the mean profile looks like for a particular type of system, for a major hurricane, for Category 1, for system over cool water, for system over warm water. And we have these standard adjustments which are based upon a mean profile. And we've gotten this over a period of time. And so that's what we say here. We begin with a standard adjustment. And the question is, did the aircraft sample the highest winds? And there's a typical undersampling, which is included in the standard adjustment. And I mentioned this before, were the highest winds that were sampled representative of the cyclone circulation, or was it part of a transient feature? If it's part of a transient feature, we do not count that as being part of it not being representative of the absolute intensity. And these adjustment factors, they will vary, and they go anywhere between 70 and 100%. You'll see us refer to these in our discussions. But one of the reasons we might depart from them is perhaps it depends on the vigor of the convection around the center, the eyewall structure, which we're able to see. This is a typical profile here. And there are low-level stability concerns if a system is over cool water, whether the winds are actually making it to the surface. We've seen this many times. So we oftentimes, with all these data, have quite a bit of contradictory data. And this is a classic example. I wanted to throw this out here to give you a flavor for what it is that we deal with in real time. This is from Hurricane Isabel, 17Z on the 18th of September. The first thing that we had was the recon pressure, which came in that afternoon. We had 957 millibars, which from the typical pressure-wind relationship gives us 105 knots. We think, okay, well, that's what we're going to use. But then we look at a time series of the reconnaissance winds. These are the peak flight level winds from that morning at around 10 or 11 Zulu, all the way up until most recently. You can see they have varied. And when we use the 90% rule, we're talking about what, 98, 100 knots, 87 knots, 106 knots. But this is actually very important right here. The dropsondes, we're looking at the peak observed surface wind, and we have these measures called WL150, which is, these are the mean winds over the lowest 150 meters. And then we have what's called the MBL, the mean boundary layer winds. And you notice that in this case, they're quite a bit lower. And one of the reasons for that is, at this point, Isabel was moving over cooler water, and so there are some stability considerations. And the SFMR measured 90 knots. In this case, the intensity was characterized as 90 knots. But quite a bit of contradictory information, and we have to arrive at one single answer. And in this case, what was most important was what actually was reaching the surface. So to construct the wind radii, this is the next part. How big is the storm? We do this in the following fashion, the 4 quadrants. The wind radius is basically defined as the largest distance from the center of the tropical cyclone, and we do this, of course, for 34, 50, and 60 knot winds. Here's an example of Isidore back in 2002, right off the mouth of the Mississippi River. And one of the limitations of the 4 quadrant radii is that, at least over water, that works pretty well. You notice that there are some gale force winds here on the northeast side, but as you get over land, that does break down, and so the winds that the winds that we've estimated, or the radii that we've estimated, are not so good over land because of frictional effects. So here's the radius of 34 knot winds, and then you notice inland we're seeing maybe 15 or 20 knots of wind at most. And to determine the size of storms, we use not only the aircraft data, but we don't always have that. We use information from ships and land stations, but we have, in recent years, we're relying very heavily on the scatterometer data. Again, we only get 2 passes a day at most over most systems, and that's if we're lucky. And we do also get some passive microwave imagery, which can be very helpful. So in the forecast process, after we've located the cyclone center and determined its motion intensity and its size, we begin to initialize and then retrieve the guidance models. This is the template that we use within what is known as the ATCF, the Automated Tropical Cyclone Forecast System. And in here, we specify the latitude, longitude, the maximum wind and its motion. We then give the RMW, the radius of maximum winds, whether the vertical extent of the circulation, how deep is it? Is it shallow, medium, or deep? And a few other parameters here. And we also specify the size of the storm at the very end. And after we do that, we've initialized the guidance and then retrieve the guidance, and we begin constructing the track. Intensity and wind radii forecast. So this is how it looks in real time here. This is Max Mayfield and Billy Wagner, one of the emergency managers for Monroe County, and here's Richard Past, one of the senior forecasters, busy at work trying to develop a forecast package for a particular storm. The steps that we consider in preparing the forecast are not very complicated.